Okay, so welcome to the 18th video in the Discrete Structures series, and this video is going to be a discussion on the Chinese remainder theorem. And this theorem is used to solve a system of linear congruences. Therefore, in order to apply and understand this theorem, it is important to understand the linear congruences first. And we have discussed this in our last video as any congruence of the form AX is congruent to B mod M. And just for you guys to recall, on the last video, we also looked into an example. 3x is congruent to 4 mod 7. And we saw that all it was asking was a very basic question. What can I multiply 3 with so that the remainder is 4 when divided by 7? And in the last video, we saw that the answer to this question would be a 6. Because 6 is the least number that I can substitute for x. And 6 times 3 would result into 18, which when divided by 7 leaves a remainder of 4. And we also went on to say that our solution was not just 6 but anything 6 mod 7. Because my original solution oscillates on mod 7, I can also assume that this solution would oscillate on the same frequency of mod 7. Therefore, 6 plus any multiple of 7 would also be a solution, and that would generate other solutions like 13, 20 and so on. And then at the end we concluded that the solution would be anything congruent to 6 modulo 7. So if we look into this process, what we really did was just to remove the coefficient 3 from this equation. So solving one linear congruence only makes sense in context of removing this coefficient of 3. And once I remove this 3 and achieve this solution, it allows me to generate a family of numbers that satisfy this given equation. So in that sense, there is nothing really to do in order to solve a linear congruence. If you consider the coefficient, as long as that coefficient has been normalized like it is here, you can already consider it solved. But what happens if I don't just have one equation here? Let's say I need a number which leaves a remainder of 6 when divided by 7. But at the same time, I need that number to leave a remainder of 4 when divided by 11. So can you think of one number that will satisfy both of these equations? So that is the entire point of the video. These are called system of linear congruences, and we will use the Chinese remainder theorem in order to find the solution to these types of equations. Okay, so let's look into a typical problem that you can see in the Chinese remainder theorem. And legend goes that this particular question comes from the 1st century from a person named Sun Tzu. And can you guess where this person is from? And I would guess China, because obviously Chinese remainder theorem. Okay, and the question goes like this. There are certain things whose number is unknown. When divided by 3, the remainder is 2. Divide by 5 and the remainder is 3. And divide by 7 and the remainder is 2. And what is the number of those things? Honestly, this is a pretty lengthy way to ask a pretty simple question, but we have our toolkit with us. So let's formalize this. All this question is asking is to find the x that is congruent to 2 mod 3 number when divided by 3 leaves a remainder of 2. And similarly, it has given me two other congruences. So x is congruent to 3 mod 5 and similarly x is congruent to 2 mod 7. Okay. And before I show you the solution, I want to mention a few things that are really important to understand. The first thing that I'll give you is an spoiler. The answer is 23. And I'll check one for you guys. 23 when divided by 3. 3 times 7 is 21 and that leaves a remainder of 2. And you can check that it works similarly for this and this. But the point that I'm trying to make here is, I want you guys to consider the product of these modulo factors. So if I take the product, 3 times 5 is 15 and 15 times 7 is 105. And the observation that I want to make is 105 is divisible by all 3, 5 and 7. Therefore, these congruences would hold on the cycle of 105. And a simpler way to say the same thing is, if 23 works as a solution, so does 23 plus 105 or 105 into 2 or anything for that matter. And this obviously happens because we see that 23 satisfies this equation. I have not shown you how we can reach to this solution of 23 yet, but considering that we can reach to a solution of 23, you guys should be able to see that since 105 is an exact multiple of 3, adding cycles of 105 still results to a valid solution. And if it were just this equation, adding any multiple of 3 would result to a valid solution. But here I'm looking at a system. I want to choose a modulus that works with all the given congruences. Therefore, the factor that I want to choose is going to be the product of all the congruences. So once we figure out the primary solution to these, 23, using our Chinese remainder theorem, we're going to say the result is 23 mod 105. Okay, this is what we're going to do. And so the Chinese remainder theorem is going to be about finding the number 23. And the real strike here would be to say that the result is any x that is congruent to 23 mod 105. Okay, so you should not be confused by seeing that the final answer is also an equation. All this is saying is that the answer is 23 or 23 added with any cycles of 105. Okay, and there's one more criteria for the Chinese remainder theorem to apply, that your modulo factors should be co-prime. You see the factors 3, 5 and 7 here. This should be co-prime. And what does co-prime mean again? None of these numbers should share any factors, right? So 3, 5 and 7 are already prime, so they don't share any factors. But you should understand the concept that numbers like 16 and 9 are also co-prime, because 16 is 2 to the power 4 and 9 is 3 squared. Okay, so these are just 2s, these are just 3s, no factors shared here. So these two numbers are co-prime, and whenever I'm given these congruences to solve the Chinese remainder theorem, I want to make sure that my modulo factors are pairwise relatively prime. Meaning if I take any two out of these three or any number of those that are given, every pair should ensure this property that they should not share a factor. And let me show you a counter example to demonstrate what happens if the factor is shared. So let's say I say x congruent to 1 mod 4 and x congruent to 2 mod 6. Okay, and 4 and 6 are not pairwise relatively prime because they share a factor of 2. In order to be pairwise relatively prime, their GCD must be 1 and not 2. And in this case, I could show you that this has no solution, because all this is saying is the list of numbers that have a remainder of 1 when divided by 4. So that's going to be 1, 5, 9, 13 and so on. And this one is going to be all numbers that leave a remainder of 2 when divided by 6. So these are going to be numbers 2 above the multiple of 6. So 2, 8, 14, 20 and so on. And you can see this will always generate odd numbers and this will always generate even numbers. And therefore there will never be a collision between these two sequences. And so there will never be a number that can solve both of these equations. So a solution is not possible. And here is another important point, and many people get this wrong. The Chinese remainder theorem is not saying that a solution cannot exist if these numbers are not co-prime. If I convert this 1 into a 2, I could immediately see that 2 is one solution to these equations. And so is 14. Because 14 leaves the same remainder when divided by 4 and 6, both of them are 2. Okay, so the Chinese remainder theorem is not denying the existence of solutions if these numbers are not co-prime. It is only saying that the uniqueness of solutions cannot be guaranteed in all cases if this is not true. But if the numbers are co-prime, a unique solution can be guaranteed. And that solution is gonna cycle in whatever their product is. In this case, 105. Okay, with all of these ideas in place, now let's look at how we actually find the solution to this problem. So let me get a little bit of space. So sometimes you'll be asked just the Chinese remainder theorem, okay, analytically. And sometimes they'll give you numerical problems. So you want to be prepared for both of them. And on the numerical side, I'll put my previous problem. Alright, so the first thing that we're going to do is to take the product of all of these modulo factors, because we know that our solution is going to repeat in that cycle. And I want to call that the uppercase M, and that is going to be the product of all my moduli. So M1, M2, M3 and so on. So this is step 1, and let me do the same thing here. My capital M would just be 3 times 5 times 7, and that is 105. Okay, now the second step that I want to follow is to consider the product of every moduli except itself. So I'm going to call it Mi, and it's going to be M by Mi. So it's going to be really clear over here at the numerical side. So all I'm doing is calculating M1, M2 and M3. And you should understand that M1 corresponds to this equation, M2 corresponds to this one, and M3 corresponds to this equation. So when I'm calculating M1, I want to take the total modulus factor M, 105, and divide it by the current modulus, 3. Okay, divided by 3, and this gives me a 35. And similarly, this is going to be a 105 divided by a 5, and this is going to result to a 21. And M3 is going to be the same 105 divided by 7 this time, and this is going to result to 15. Okay, so this is M1, this is M2 and this is M3. And I think understanding this will help here. See what we are doing here. This 35 is actually the product of 7 and 5. So for the first modulus here, I want to multiply the other two, 7 and 5, okay, and that is 35. For the second one, I'm multiplying the first and third. See, 3 times 7, and that is 21. For the third one, I'm multiplying the remaining 2. This 15 is this 3 times this 5. But since we have already calculated the product of all 3 moduli, it is just easy to divide with the respective modulus. Okay, since this was 3 times 5 times 7, in order to calculate 5 times 7, I'm dividing a 105 divided by 3. That's all I'm doing here. But you should know that the logic of dividing 105 divided by 3 comes from the fact that I want to take the product of all the remaining modulus except the current one. Okay, so I've completed my step 2. Let's look at step 3. So the third step is going to be finding the modulo multiplicative inverse of all of these capital MI's mod their respective small mi's. Okay, and that is the same as asking capital Mi times what leaves a remainder of 1 when divided by small mi. And this comes from the definition of modulo multiplicative inverse. And we have already seen in our past videos how we can compute the modulo multiplicative inverse of any given number mod any other given number. So if you are unsure about the process, please go back and watch the videos on linear congruences and also the extended Euclidean algorithm. But for the Chinese remainder theorem, we cannot afford to apply the Euclidean algorithm for each congruence. So we are going to have to guess this value anyway. So you can just follow along for now. Okay, so let's follow through the third step. And before doing that, you might want to formalize this because there is every possibility this might be asked in the analytical format. In that case, you just want to formalize step 3 by saying you want to solve mix congruent to 1 mod mi, and even better, you mention in paragraph that you are finding the modulo multiplicative inverse of mi mod this value. And if this is unclear or confusing you, let's look at the numeric examples to make it clear. Okay, so first I want to calculate the inverse of capital M1. So M1 inverse, that means I want to calculate the inverse of this 35 mod 3. Okay, so M1 inverse is 35 inverse mod 3. Why 3? Because this comes from my first equation. And you should know here minus 1 does not mean 1 by 35. It rather means which number can I multiply 35 with so that the remainder is 1 when divided by 3. And let's say if I take 35 on its own, dividing by 3 would give me a remainder of 2. And that is not 1. But if I multiply this 35 by 2, I get a 70. And 3 goes up to 60 and 66 and 69, right? And that leaves a remainder of 1 whenever it is 70. And therefore 2 is the modulo multiplicative inverse of 35. Okay, let me erase all the rough sketches. And we know that this is equal to 2. Similarly, next I want to calculate 21 mod 5. And next I want to calculate 15 mod 7. So let's do that. M2 inverse is going to be the inverse of 21 mod 5. And again, what can I multiply 21 with? Well, it already leaves a remainder of 1 because 5 times 4 is 20 and it's already leaving a remainder of 1. Therefore, I can simply multiply this with a 1. So the result is just a 1 here. And similarly, the inverse of M3 would be the inverse of 15 mod 7. And this is also equal to 1. Because 15 times 1 is just 15 and that when divided by 7 leaves a remainder of 1. Okay, so I have successfully calculated the modular multiplicative inverses of these numbers 35, 21 and 15. And therefore I have completed step 3. Alright, and the last step is to use this rule. Once I've calculated these values, I can express my solution x as being congruent to. And the idea is that for each of these congruences, you take the modular inverse first. You multiply that with this number, the product of other moduli. And then you multiply again with your remainder. Okay, so assuming my remainders are a1, a2 and a3 and so on. My solution would simply be x is congruent to m1 inverse times m1 times a1. Okay, simple as that. Take the inverse, multiply it with whose inverse you calculated, and then multiply it with the remainder from your original equation from over here. And so the other terms would be m2 inverse, m2, a2, and then this would continue. And like we discussed at the very start, my solution is this thing mod the product of all my moduluses. So the very capital M. So if the question just asks you about the Chinese remainder theorem, you want to consider your own equations a1 mod m1, a2 mod m2, a3 mod m3, and you can follow these steps and leave the solution at this point. But for my numerical example, let me complete this all the way. Okay, so from here on out, I know that my final solution x is congruent to. So I'll take the first inverse, that is 2, multiply it with the corresponding product of other moduli, the m value here, that is 35. So times 35, and then multiply that with the remainder from the original equation. So that is 2. And I'll do same for the second equation. That will give me 1 times 21 times 3. So I'll write here 21 times 3. So of course you have a plus here. And the last one is going to be 1 times 15 times 2. So 1 times 15 times 2. Okay. And this is congruent to Let me do some arithmetic here. Okay, and we discussed in the very first part of the video that my solution is going to be 233 mod 105 because that is my full cycle, and therefore I can reduce this, right? 105 times 2 is 210, and if I take the difference, I get 23. So I could simplify this by saying x is congruent to 23 mod 105. So like I promised you in the original premise of the video, 23 is one such number which satisfies all those given congruences. And therefore 23 plus any linear combination of 105 would also satisfy the same equation. Alright, so that concludes the discussion for this video, linear congruences and the Chinese remainder theorem. We'll close this chapter in the next video with a look into the operations on large integers and 0-1 matrices. And those are also called Boolean matrices. So I'll see you guys with the discussion on the next one. And until then, have a good day and bye.